Hello everybody, this is Mr. Zimbrick. Today we're going to be talking about what holds matter together. This is part 2 of the building blocks of life. I posted part 1. It was for the foundational biology class. If that's something you want to go back and review, you can look at it. If you looked at the slides and you feel like you're ready to jump into this, then let's go ahead and do that. So anyway, we're going to be talking about bonds, chemical bonds today, and what we're going to do today for notes is I want to kind of just get a little bit of a formative assessment of where you guys are with your notes. So you're going to be able to freeform your notes today however you want, and I'm going to be giving you your notebook check on Friday. So I want to see what you guys or how you guys would like to take notes, what works for you, and maybe if your note taking needs a little extra help. So do whatever you would normally do to take notes, and then we'll look at it together on Monday after I do the notebook check and see how you did. All right, so without any further ado, our essential question for this lesson is going to be, how do atoms stick together? And that's sort of the simple way of saying what are the different types of chemical bonds and what makes them different, or how are they similar? That's going to be our essential question. That's our learning intention that we're shooting for today. Now we've seen this picture of the atom before. Inside of every atom, we know there are protons, there are neutrons in the nucleus, and then there are electrons orbiting around in this cloud outside of it. The protons have a positive charge, and there has to be an equal number of electrons orbiting around to create a neutral atom. What we're going to find out today is that not all atoms need to be neutral, and in fact, if all atoms were only neutral, we wouldn't have life. The ability for electrons to jump around is very important for life, and that's what we're going to talk about. So in the case of helium here, we have 2 protons and 2 electrons, completely neutral atom. I want to talk a little bit more about electrons and how they orbit around in an atom. They actually don't go around the atom like the planets around the sun. That's sort of a misconception that a lot of people have. However, it does help us make sense of some of the things that we see happening with atoms. So it's easy to draw it like this, and we can make sense of it. But you have to remember that it's not an actual representation of reality. So we have this two-dimensional image here of a hydrogen atom, and we have 1 electron floating around it. In this case, this H represents the nucleus. That's going to be the proton. And then we have 1 little lonely electron going around it. In reality, it wouldn't look like this, but we're going to use this model to demonstrate some ideas today. So in every atom, there are these electron orbitals. And we talked about last quarter how, if you did the atoms unit, how electrons can bounce between these orbitals here. And it turns out that in this first orbital, where electrons can occupy space, only 2 electrons are allowed. There's only 2 electrons allowed in here. And then if for some reason a third electron were to come in, it would actually go up to this second energy level, and it would go orbit in that energy level. So this first energy level can only hold 2 electrons, the second one can hold 8, and the third one can hold 8. And it turns out that most atoms, they want to have their outermost orbital full. And we're going to take a look at this concept in a second. But quickly, I just want to try pointing out something here. So if we have hydrogen here, if instead of hydrogen we had something like helium, so I'm going to try drawing this here, helium, He instead, well then we would have 2 electrons. So we'd have this electron and this electron in this innermost circle. And that would mean that its outer shell is completely full. Okay? If instead we didn't have helium, but we had, let's say, we have lithium. If this were lithium instead, Li, then we're going to have 2 electrons on this inner shell. And then the third electron, because lithium has 3 protons, is going to have to bounce out to this next energy level. So in the case of lithium, we have a full inner shell with these 2 electrons, and then the next electron shell is going to have 1 electron in it. The idea here is that electron shells will always fill from the innermost shell to the outermost. Okay, so keep that in mind as we go forward here. Okay, now I'm going to introduce you to a concept of something called the valence shell. The outermost shell of any electron orbital on any atom is called the valence shell. So the valence shell is the orbital where electrons can come and go. They might jump off of this carbon atom here and go over to a hydrogen atom, or they might come from a hydrogen atom, jump on to the carbon orbital, and then go back and forth. And these electrons, they're very slippery, they're moving very quickly, and they move all around. And it's in the valence shell where all sorts of really fun things happen in chemistry. And that's where we're going to focus on today, is this valence shell. In the case of carbon, it's this outer ring here, and carbon has 4 electrons in its valence shell. So the valence shell is it's the outermost shell of any atom. Okay, so we got a lot of information here. What this diagram depicts are various elements in the periodic table and their electron configuration. So in the red is the valence shell of each different atom in different elements. So we can see which electrons are going to be available for forming bonds. Earlier, or you may have seen in part 1, we talked about bonds can happen when different elements stick together. We're going to learn about the specifics of how that happens here. So valence shells prefer to be full. They're more stable when they're full. So elements in group 1 over here, hydrogen, lithium, and sodium, they have just 1 electron in their valence shell. And so the shell that's underneath is already full. So it's very happy like that. And this little electron floating around outside of it, well, there's not a lot of electrical force there to hold it in. So that electron is actually going to go jumping around to all sorts of different atoms that might be nearby. Because it's not being held in. It's more stable with a full valence shell. So we can imagine in this lithium ion, or this lithium atom, if it loses this electron, then it's going to have a full 2 in its valence shell. On the opposite end of the spectrum, we have these atoms in group 17, like fluoride and chloride. Oops. Where we have 7 electrons, and they want to be full with 8. So these ones are desperate for electrons, and these ones are willing to give up an electron. Okay? And the idea here is that no matter what your valence shell is, you're going to be trying to fill it up. So this one is going to be looking for electrons. This one's going to be trying to give it off. We have this octet rule, which is a rule in chemistry, which says that valence shells are going to be more stable when they're occupied by 8 electrons. So anytime we come across different compounds, we're going to find out that the number of bonds it can make is dependent on its valence shell. So if we look at group 18 here, and we look at its valence shell, helium's got 2 in its first orbital, so that one's full. We've got neon here, it's got 8 in its valence shell, so it's full. And then we have argon, also has 8. These are all called the noble gases, and they have full valence shells. What do you think is going to happen with these atoms? Do you think they're going to be likely to bond? We know that fluoride, or fluorine, is going to want to get another electron to fill up its orbital. But this one's already full. So what do you think might happen with that one? That's something for you to think about. Okay, so a little bit more about this octet rule. Kind of figure out where to put myself. The octet rule says that valence shells all want to have 8 electrons. And atoms are going to bond by sharing their electrons to fill their valence shell. They can actually split time between electrons, essentially. So when atoms share electrons, we call that a bond. And there's different kinds of bonds that happen. The first one we're going to talk about is called a covalent bond. And this is when atoms are sharing the electrons. The electrons are flying back and forth between 2 different atoms. In the case of oxygen here, oxygen has 1, 2, 3, 4, 5, 6 in its valence shell. So 6 plus 6, it only equals 12. But we can actually share 2 atoms for each of them. So if we count here, 1, 2, 3, 4, 5, 6, 7, 8, this one has 8, and then since it's sharing, this one also has 8 because of the bond that's happening right here. And so when we talk about covalent bonds, that's what we mean. These electrons are being shared by 2 different oxygen atoms, and they're fulfilling their octet rule because now they both have 8 in their outer shell and they're bonded. That's called a covalent bond when atoms share electrons. Here we're going to look at the same idea, this time with a compound, a special compound to all of us known as water. And again, we've got oxygen, which has 6 electrons in its valence shell. So it's trying to find 2 extra electrons to fill it up to get to 8. In this case, it finds 2 hydrogen atoms, and they each share their 1 electron with it. So 2 electrons are coming in, 1 each from these hydrogen atoms. And now if we count around oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So now oxygen is very happy, its valence shell is filled up, and it has these 2 hydrogen atoms that are now bonded with it covalently. Covalent bond, again, is when electrons are shared between the atoms. So we've got an electron being shared between oxygen and hydrogen in both of these cases. And that's how water forms. Water is a molecule, it's a compound. The second type of bonding is something called ionic bonds. Ionic bonding occurs when an element with only 1 or 2 electrons in its outermost shell donates an electron to an element with 6 or 7. The picture at the top here shows sodium donating. It gives up its electron to chlorine. In this case, sodium is more stable without its outer electron, while chlorine is desperate for one more because it already has 7. And it's going to be much more happy with a full valence shell. And when it's done that, it's satisfied its octet rule. And when this happens, here's our products. We have a sodium with a positive charge. We call that a cation. And then we have chloride with a negative charge, which we call an anion. So now we go from 2 neutral atoms to 2 that are, one has a positive and one has a negative. So again, if you add them up, it's still going to be neutral on the whole, but now they're ionically bonded because sodium has given up its electron to chlorine. And they have both satisfied their octet rule. And that's called ionic bonding. Now we're going to watch a little video that shows this in action. Again, in reality, it's going to look different than this. This is just a good way for us to visualize what ionic and covalent bonds look like.
Ionic bonding occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay, so that just showed you the difference between ionic and covalent bonding. We said earlier that covalent bonding happens when atoms are sharing electrons, as happened in water, and you could see the electron flying from the oxygen atom over to the hydrogen one and back and forth, and they're interchanging, and that's what a covalent bond is. Well, in the ionic bond, the chloride or the chlorine wanted or had a stronger charge, so it completely pulled off that electron from the sodium atom, and that's what an ionic bond was. So in an ionic bond, there's no sharing of electrons. It's pretty much just like a vacuum sucking it right off of the sodium atom. That's the difference. Okay. Now, what I like to do at the end of every lesson is do a little summary of everything we learned. So let's look at the essential question that we started with. What are the different types of chemical bonds? What makes them different, and how are they similar? I think a good place for you to stop would be right now and just think in your own head, could you answer that question? But I do have a little write-up here if you want to review that you can read over. I'm also going to post into the Moodle some additional readings if you want to get more information about ionic and covalent bonding. We're going to be using an OpenStax textbook that I will link to in Moodle. So what you're going to do now is you're going to find the processing assignment at the front of the room for intermediate or advanced biology. It's got 3 questions on it that you can try to answer. They're mainly just drawing up some of these electron diagrams and using the octet rule to figure out how the bonding is going to work between different atoms. So it's just a few questions, and what I want you to do is answer them to the best of your ability, and then use either these slides or the textbook reading to answer them. When you're done with that, what you can do is go ahead and work on your poster assignment. So that's all I have for you today. You guys can start on your processing assignment. Thanks for listening, and I will see you tomorrow.